found the 2D process for interpreting statistical isotropy.
Okay. First of all, let me make a comment on CITA and Dick Bond. So, the first interaction with Dick was a phone call that I received around 11 in the night to get the job offer from CITA. And I was very excited, and my only task in the phone call was not to give up, that I would accept immediately. Pretend, oh yeah, think about it. Because CITA was really the number one in my list, and I'm very happy I came here, and I'm always very happy to have this. The topic I'm going to discuss today is about the idea of breaking statistical isotropy from the model point of view. This is work in collaboration with Lev, Carlo, and two of my students who have very difficult surnames. So. I call them by name. You know, there has been a number of CMB anomalies, and I don't have time to review them here, so I'm just listing them here. And there is a problem, as you know, because there is a lot of paper discussing them. And I think the main problem is that it's very hard to assess the a posteriori significance. So whether something is significant or not depends on the statistics you do, as we saw in the previous talk. And if you do a lot of statistics, a few of them will fail just because of statistics. And so it's very hard. Although it doesn't mean that these effects are not there, but it just means that this generates a lot of discussion. And if you want to have a summary with actually a negative assessment for almost all of them, you can look at the last WMAP paper, which has at least very good reference and very good overall discussion. I'm going to concentrate in one of these effects, which is the breaking of the rotational invariance. And my interest was triggered in this paper in 2008, where they studied what is called the axiomatic Caroline-Wise model, which is a potential, a primordial potential, which has an angular dependence. And it's come from this paper. And actually, just to make things straight from the start, this model is unstable. At least this is what I call a model. In my opinion, a model is something which has a Lagrangian, and everything comes from the Lagrangian. So if this is your definition of a model, this is not a good model. But there are other people who have different definitions of models, and they call just model parameterizations, which is not what they do. But in this definition of a model, this is an interesting thing to study, because this is... No, I'm saying it's good that there are people who do analysis based on templates, right? It's a very interesting parameterization, so let me say it. And the idea is that you do a Taylor expansion, and V is a privileged direction. This will be the first term that you get if you assume that you have 2D isotropy. And in this analysis, in 2008, it seems things are pretty interesting, because you see, if you look at this was the only two bands that we were showing of WMAP. They both signal that the G star should be different from 0. And one effect is about 4 sigma. And what is particularly interesting is that the effect piles up as you increase the number of L's. You see, the red line is for L up to 100. Instead, when you go to L up to 400, the effect increases. And this is due to just to sample variance. It was actually theoretically predicted in this paper. So the situation looked to me particularly interesting, because in the light of Planck, right, if the effect is there, you would just guess that it's going to be much more significant. The problem is that this analysis is wrong. It was realized in this paper I cited there that they missed a factor in the covariance matrix. Not that they took it from another paper, but the point is that there was a missing factor. So once you redo the analysis, actually the significance becomes much greater for one of the channels. The first channel is a 9 sigma detection. But you still start seeing a lot of things that you don't like. First of all, that there is no consistency between different channels. And second, that the privileged direction now comes up to be exactly coincident with the ecliptic direction. This makes you smell that probably this is systematic, not really cosmology. This was not the case for the previous analysis. However, it's very hard to study systematics effect, in the sense that when you read the paper, some paper like the WMAP paper claim is for sure asymmetric beams. When you start reading the Gurlenberg et al. Paper, you say, oh, we tried asymmetric beams and it didn't work. So, as a theorist, I really cannot say anything like that, unless just to say we'll wait for Planck, because of course there's going to get differences in mathematics. And so as a theorist, I'm just trying to be interested in whether there are really concrete models that can give these signals, models where I say start from other times. And the short answer is no, as I'm going to just explain now. So what is the idea? The idea is since there is maybe a breaking of rotation imbalance, let's take a metric that does so. This is the Yankee metric, the simplest Yankee metric. And the question is this enough to have the signal which was played by Ackermann? And this was the question that I asked myself when I started this series of research. How many modes there are in the perturbations for this geometry, how do they behave, and what are the physical signatures? And the number of modes is the same as in Finner-Robertson-Walker geometry. And here it's just a very simple counting of modes. You have 11 modes. Here I'm discussing the case where there is one Newton field. So you have 11 modes, 4 of them are eliminated by general coordinate transformations, 4 of them are non-dynamic, you end up with the usual 3 modes. However, what is the difference is that they are coupled to each other provided the linearized value. So when there is a fewer symmetries in the background, you're going to get more couplings. And what does it give me? Well, first of all, a non-diagonal correlation matrix. This is very good. This is in the same idea of Ackermann and Tarun. But it also gives new things which I was opting to make predictions. It gives tensor scalar correlations. And then it also gives different results for the two gravity wave polarizations. So in principle, well, if one can manage to find a self-consistent complete picture, you could be able to do other predictions rather than just the in the power spectrum. And this is the first thing that we studied. We studied the simplest thing you can imagine, where you put just an initial and isotropic condition. And this is the universe which is going isotropization thanks to the Isotropy field. So you see, right, the Isotropy is very powerful, so within 1 Hubble time it's going to isotropize the universe. And there is, however, an initial singularity, which you can see there on the left, is a Kasner singularity. And there are some interesting phenomenology that in principle can come from here, because the Kasner spaces are unstable. And so during the Kasner epoch, the one that takes place on the left, there is some instability, and we found that this instability is associated to the growth of one gravity wave polarization. The growth is really interesting because it occurs only on large scales. So in red I'm showing large scales, very large scale mode, in green intermediate, and in blue small scale mode. During Kasner, the universe, the modes go from large scale to small scale. And then you see on the left that some power can grow on very large scales, and you see at the end you get a very different order of magnitude result. And also you see at the right that the instability ceases when the universe becomes inflationary. So in principle you have a large growth that could take place before inflation, which in principle, if you're optimist, could give you a large gravity wave signal. But of course, what is the trouble is that you don't really have much theoretical control. Because you see the isotropic stage is next to the singularity. And so it's very hard to give initial conditions. Indeed, I don't really have a predictive way to give initial conditions. So the mathematics works, but physics is not rich enough. And one has to look for a richer physics. And there is a beautiful short and so beautiful theorem by Wald which discusses isotropization of Bianchi spaces when you put a cosmological constant plus a source that satisfies dominant and strong energy condition. Almost all Bianchi spaces immediately isotropize. So in order to make it work, you need to violate the premises of Wald's paper. And the literature gave counterexamples. You can do it with axioms, you can do it with higher curvature terms. But most of the examples, which are the simplest one, are given with vectors. And you can notice that there is a number of models with vectors which were proposed recently, just motivated by the phenomenon. My contribution on the field, I'm sorry, is to show that all these models are unstable. So the models in the vector field. I wish I would have other conclusions, but that's what I found. And I don't really want to discuss all the cases because otherwise the chairman will not be happy, neither would you. But let me just discuss briefly the philosophy and the simple situation. You see, what is the idea? You know very well that when you have a vector field, the vector field goes to zero immediately as the universe expands. And so we will not be able to give an isotropy. The idea is that we give a special vector to the vector. But we must make sure that the vector doesn't go to zero immediately. So in a sense, you have to modify the action of the vector in such a way that the vector is in a slower origin. And this is exactly what, these are three different ways of achieving this. And I will discuss only one of these three ways. So you see, I'm giving a value to the vector in the x direction, and then little h is the anisotropy in the expansion rate, which I assume to be smaller than capital H. And then you'll see that you generate an anisotropy now which is proportional to the value of the vector. And now, the standard case is when there is no coupling to the curvature, size equals 0. If you take size equals 0, you see the vector gets an effective mass term, and this is what drives the vector value to 0. However, there was the clever choice to choose size equals 1/6. If you make this choice, the mass term disappears, and now the vector gives a slower evolution. This is actually the first paper by this that I know was a mechanism by Turner and Widrow for generation of primordial magnetic field, which is also unstable, what I'm going to tell you in a moment. The trouble is the following, that you get the wrong sign for the mass term of the vector. So in order for having the mass term to cancel, the effective mass term, you need to start with a plus sign over there. And you know, if this was a scalar field, you would tell me, okay, not a big deal, I just have a tactor. But I have a wrong mass term for a vector field. What does it mean? It means that I have a field which is a ghost. And why do you see so? A ghost is a field with wrong kinetic term. Here you see I'm using signature minus, so a plus sign here is a wrong kinetic term. And here is a mathematical way to understand this, but conceptually is the following. You know, if there is no mass term, the vector has only 2 degrees of freedom, the transverse mass. But when you have a mass term, you have a third degree of freedom. But of course, the nature of this degree of freedom is controlled by the mass term itself, because this is the one that generates the third degree of freedom. If the masses are wrong, the term is the wrong sign, you get a term which intrinsically has negative energy, which is a ghost. And let me stress that this is an instability which is intrinsic on your choice of the model. Besides this simple argument, we also did a complete calculation where we added all the perturbation of the metric. It's quite a difficult exercise, but it gives us what I'm just telling you. What I'm showing there is that's the look at the red curve is the Newtonian potential, the GR Newtonian potential, which you see diverges at a finite time when the model is close to horizon proximity. So in this particular model, and actually in all of these models, all the perturbations diverge in the linearized calculation, and they diverge in a finite time. Now, of course, there are many other problems associated with having a ghost in your model. And for example, you know, if you have a ghost, the vacuum is unstable because the vacuum can just decay in ghost and ghost pair. And for example, it was shown by Klein and collaborators that if you have a ghost, just the fact that we don't see the decay today, you have to pose a limit on the validity of your field theory, and you have to put a cutoff at the MEV level. And of course, if you have a theory which is only valid below MEV, you cannot do inflation. That's not typically what we are doing inflation. And it's very hard to complete a theory. You could imagine that my theory as a ghost, that is only an effective theory, but actually, despite this, what people say, nobody has really concrete examples of a theory with a ghost which gets nicely complete. So it's certainly a big problem. The model by itself is unstable even at the classical level when you compute the equation of motion, and moreover, there is the instability at the computer. There is an idea that actually works. I just want to give it to you because it was a clever idea. The model becomes a little contrived, but it just shows you how contrived you need to be if you want to make it work. And the idea is that in this model, you don't break the one invariant, so there is no mass term for the vector, but there is an interaction with the scalar. So there is no longitudinal vector, but this f of phi is the inclusion field, which is coupled to a vector. And this f of phi will make the vector evolve in such a way that you still get an result. And I don't want to go too much into the details, but there is a Souradeep condition. And then you see that if you manage, you have to coop the model. Because you have the energy density in the vector needs to scale the same way as the energy density in the scalar field. In this way, you have a prolonged isotropy. But then A is increasing exponentially, so F has to decrease exponentially. And so it will make F to be an exponential function of the entropy field. And you can play with the parameter. You can get a regime where you have a smaller isotropy. And these are just the power spectra that I'm showing you. And I'll be quick. but there is the scalar correlation function on the left part, which you see exhibits an angular dependence. So on the right, on the x-axis I put in the scale, on the y-axis the power, and then psi is just the cosine of the angle with respect to the privileged direction. So you see that there is a scale dependence in the spectrum, but also you see that you generate the tensor correlation function and also scalar tensor correlation function. I was hoping, everyone was hoping to get a large scalar tensor correlation function, but actually when you put realistic numbers, you find that it is not the case. So even if in principle there may be an interesting signature in the tensor scalar correlation, most likely it's unobservable because it's smaller than the tensor. So I'm concluding. As I said, there is a number of anomalies, and why do we use the word anomaly, right? We use the word anomaly because they don't come in the simplest version of our models. And but the question we ask from the theory point of view is how easy we can make them, right? Because if it was so easy to make these models, then we shouldn't call them anomalies. However, our attempt showed that actually it is rather harder than what other people are. Okay, thank you.
So, did you say that there aren't any models in which you can go into the ghost mode and then back into reality with the sign changing, so no real multiplier?
That's my statement. I wish so. The problem is that when you change the sign, you enter in a strong gravity regime, and this is the moment where everything diverges. So when the sign is strictly zero, no, but when you are going to the limit, the sign goes to zero, you are going in a regime where it's strong gravity, just because you have to canonically normalize everything. And actually, this is the moment where everything goes up.
So what's your take on W less than -1, which is relying on negative kinetic energy over at least some region often?
My personal opinion is that I don't like this.
No, but there's no effective realization. So
yeah, exactly. One has to walk, right?
So a theoretical prior should say thou shalt not let W go less than -1.
This is my theoretical prior. There may be other theorists who are more brave than me. My own prior is I put a line here and I don't look.
There's a recent paper by Duncan Hansen and Chapman and Lewis that looked very carefully at the effect of looking at linear symmetries. And they see it accounts for the number and it works numerically detected by a detector. So there's very strong evidence.
This was a later paper is on my staff, and okay, now I have a reason not to read it. Thanks.
It's a wonderful paper.
Very good.
So let me begin by saying I'm very happy to be able to come for this CITA 25 big SSC, and it's great to be here. So what I'll be talking about is statistical isotropy of CMB fluctuation. I added this little bit of evolution of statistical isotropy, and it has two connotations. One is that the evolution of my ideas in this, which started with work that I did with Dick and Dimitri on topological, constrained topology of the universe. And the basic idea was that I wanted to look at ways of getting it without really worrying about orientation of the space. That's how I got into this. And I first presented this work in 2000, CITA 2K, from which I got a lot of inputs from Dick, and happy about that. That's how this is taken up. So the thing that I'll be talking about today specifically is the work that I recently did with one of my students, Mohammed. And this is to look at how these statistical isotropy violations early in the universe would propagate to the present universe. Okay. So just to set the stage, I mean, you know that the CMB comes to us from basically like a IMAX skater around us, and it's the easiest way to see that this is probably the arena in which you should be able to detect any violations of rotational symmetry in the universe. You know, the largest scale, and the CMB anisotropy comes almost unimpeded from the last scattering surface, except for the ionization and lines of blue. So the basic focus of my talk is to ask, if I see statistical isotropy violation in the present day CMB distribution, how do I relate it to what happened on at a much simpler stage of the universe when the entire thing was just a barrel of photon fluid. And so many people have talked about it, so there are sort of motivations for looking at statistical isotropy violation because there are so-called anomalies. What I wanted to really point out is that all of these can be put into one single bin by saying these are basically a breakdown of statistical isotropy. The CMB sky is not invariant statistically under rotations with the sky. So, and that sort of helps in trying to see what you want to look at. So what I'll be looking at are basically statistically anisotropic but Gaussian fluctuations, whereas this is also possible. And this field has a history before I got to it. So the basic idea is that the 2-point correlation of the same fluctuation is no longer just a function of the angular separation between the two directions you're looking at. And you need to really expand your repertoire to sort of address that. And an example I picked up from, again, work that I did with Dick and Dimitri on hyperbolic universes, sort of shows what we mean by breakdown of statistical isotropy. Here is a nearly statistical isotropic CMB sky. What I'm plotting here is the correlation function from the North Pole, and you can see circularly symmetric contours which tell you that the CMB correlations are isotropic around it. As I break down isotropy, you can see the contours distort and they can even break out into multiple images. And if you have been to the talks in the same session by Amir and Dimitri and Andrew, you will see nice pictures of this. The question is, these could be sort of ugly things like a violation of some Pauli principle, or it could be beautiful correlation patterns. Stella had pointed out the connection between spots on the level and beautiful correlation. The main question is, how do we detect them? And many speakers have been telling you that one of the problems in this anomalies game has been the sort of a posteriori statistics being used. I mean, you look at the data, and so you would like to go and try to come up with something which looks beyond the angular power spectrum to detect patterns in the CMB, and does it so that you not obviously sort of looked at the data and done something. So it's a mathematically well-defined formalism that you need to probably look at. And what it will give you is a handle on universe on ultra-large scale, so that includes global topology, rotations, anisotropy, breakdown of global symmetries, magnetic fields, moving magnetic fields. Or it could also be sort of a good way to measure observation artifacts, like if you have photon residuals or inhomogeneous noise or coverage of the sky, non-circular beams. All these should be all included in this. So this is again repeating a bit of what Amit mentioned, but the idea is now we need to look at a correlation function which is not something like this, where you can expand it as Legendre polynomials. But if it is just a simple function invariant separately, the most general space you need to look at, or space functions, are the bicorresponding harmonics. And what you really, these coefficients, essentially, what they are doing is essentially angular momentum sum of the ALMs that you measure in the same sky. And so this is the bipolar spherical harmonic representation that you want to look at. So what I wanted to emphasize is just like you take a CMB map and compute the ALMs and CLs. You can take a CMB map, and that's something that we've done with data, and I mean, this is some of the results. And you can compute the bipolar spherical harmonic coefficients. They are measurable, and you can sort of mod square them and add them and get a power spectrum, the bipolar power spectrum. The interesting thing about this is rotationally invariant in the sense that whether it's not sensitive to which direction your correlation function has broken asymmetry. If you have direction in the sky, it just shows up. Okay? It doesn't care about which is the direction. So this whole business of marginalizing over orientations is not really important. The main point is if there is no statistical isotropy violation, then this kappa L should be consistent 0, and all ALMs with this script L should be sort of consistent with 0 for except L equals 0. And over time we sort of added a little more to it in the sense that kappa L was completely blind to orientation, but people would probably want to, if something is detected, want to know where is the orientation of the correlation pattern. So you could sort of sum these up in various ways. The Rumor tells us that that's a particular way of beginning in L. What we proposed is something called reduced bipolars, where you just sum over these L and L prime, the spherical harmonic moments. And interesting thing about this is this has the same rotational properties as small ALMs, and you can actually make so-called correlation maps. So you can actually make a visualization of non-statistical isotropic correlations, which we call bipolar maps. If it with universal statistical isotropy, this map should just have a monopole. This should have no structure. And this is just what you get from the block 1 and 3 and the difference. It's not really relevant for what we'll talk about today. So, since I came to it from the point of view of topology, in a compact universe, you would always have the two-point correlation sort of break up in this fashion. So your modes become discrete. And this is an example from a 3D torus. And you have the simple expansion here. And if you look at the small k part of it, you would see that the correlation function would sort of acquire this kind of corrections to the at different levels, right? And what is interesting here is, what is important here to notice is for most compact topologies, these epsilons would die off with wave numbers. At large wave numbers, you'd expect them to go to 0. And that actually meant almost always that the signal would be only at large angles. Your statistical isotropy violation for these is at large angles. And as you know, that large angles is more difficult to sort of detect statistical isotropy violation because you are dominated by cost variance. But in the context of compact systems, that's what you've lived with. What is interesting is Mark Kaminkowski and then Pullen, they sort of got out of this thing and said, oh, let's have this power spectrum just be a function of of the k vector itself, and GLM you could have it to be independent of k. For example, GLM does not need to diaphragm. Of course, then the field opens up because now you get signatures that you can readily measure from the CMB map, and that's what's been going on. So if you look at this G2 measurements, it's all with k, it's independent of k. And in terms of the bipolar coefficients, it's essentially the same, except for this factor here, which sort of says that this leads to a subspace of possibilities where L prime and L, capital L, the bipolar L, have to add up to be an even number. So it's a subspace of possibilities. So if you want to go and take these bold steps, then the question is why just worry about the power spectrum being anisotropic or function of wave number? There's this even more obvious possibility that the CMB distribution function itself violates statistical isotropy. Okay? Notice that when we do CMB anisotropy, we actually have the brightness function fluctuations to be a function of k hat and e hat, the momentum and wave number directions, and you take it to be a function of k dot p. Okay? And that leads you to this Lagrange expansion and gives you the CLs. But you let that go, then of course the obvious thing to look at is a much broader, bigger space of functions here. So if you don't allow this symmetry, then you have to have bipolar functions of which are bipolar in nature, the distribution function, and actually you can directly connect ALM off-diagonal correlations in the CMB sky to statistical anisotropic terms, that is something with capital N not equal to 0, higher than 0. Okay, and there's a very nice way to connect them. And to make it look neater, you notice that the bipolar coefficient is basically a tensor product of ALMs. And so what is interesting is if you wanted to look at the most general case, you allow for the power spectrum to be anisotropic, you allow you take this not to respect the symmetry, the brightness function to be anisotropic, then basically you can predict, directly write a connection between the bipolar coefficients that you measure to tensor products of these brightness functions at this present time. So that's part one. So anytime I see a ALM A prime correlation, if it's coming from the same distribution function, it is this terms which is causing it. If it is coming from and if it is coming from the anisotropic power spectrum, then these are the G's which show it. So these incorporate the two effects. In particular, if you take the power spectrum to the isotropic, then it's a slightly simpler connection here between the anisotropic terms in the Boltzmann function and the bipolar coefficients that you measure. So that's now. And the question is, this allows you to sort of play with a lot of possibilities of how to get something that, for example, WMAP field. WMAP field is something with very specific relations between ALMs and having the bipolar coefficients. And so it's interesting to try and think of how to relate something that you see now to something that happens at the last scattering surface. And of course, again, this is something that I learned when I was here, that you can do a one-step connection between the anisotropy that you have at the last scattering surface to the anisotropy now, and this is well-known to connection between what you have, say, the monopole and the dipole of your brightness fluctuations at last scattering can be directly related to all the ion moments that you, in the angular power spectrum that you see now. This is for a statistical isotropic case. But you can do the same thing. So in the statistical isotropic case, the delta at the last scattering surface goes to a set of deltas now through this kind of a free streaming evolution. When you do it for these more generalized statistical non-statistical isotropic brightness function modes, you have a similar, more complicated but similar structure, which sort of allows you to free stream the brightness fluctuations which are anisotropic at last scattering surface to ALM correlations at the time now. Right? It's a straight connection here, and this in asymptotic limit the equations look very similar to the statistical isotropic case, and so you can look at more. The basic point here is just like you had all your anisotropy in the monopole and dipole term at the last scattering surface, and you get all the CLs now. Similarly, if you had statistical isotropic violating physics at last scattering surface, it would generate a statistically anisotropic term in the Boltzmann function, which you can free stream to large multiples and see it in the CMB sky now. Okay, so this is basically the formalism, and what is it good for? What is it good for? You can look at, for example, one of the examples we looked at long back with AMI was the statistical isotropic violation due to a primordial magnetic field at the last scattering surface, homogeneous field. And in this formalism, it's easy to read out. This has been worked out by Tuller and company, yeah. And what you can do is look at the result and look at which bipolar harmonic coefficients are present in this expression for the brightness function there, and you can directly read off what should your ALM correlations be. And we are sort of looking at other effects. This is an obvious thing which was already there, but now you can imagine the baryon photon fluid is a very simple system. So you can introduce physical effects there, look at statistics and violations of those, and then you can directly free stream them and look at what the predictions will be at this present time. The free streaming is very similar to what happens in the statistical isotropy case, only with larger bipolar molecules which sort of dies out. So I'll just put up my summary. So the main point is the bipolar harmonic representation provides a mathematically complete and verified representation of statistical isotropy biology. And it can be applied to real data, so it's being done, and both by us and the team. And well, it's possible to include violations arising from both direction-dependent primordial power spectrum, which is a lot of attention now, and we want to talk about it, as well as the other part, which is also equally possible, that you have statistical isotropy violation in the baryon photon fluid, and that's something that I talked about, and you can evolve whatever happens at the simple fluid case to what you see now by simple equations. It sort of is very illustrative. I mean, it's nice to be able to get these results right out. Thank you.
Starkman, also a different title, Troubles in Cosmological Physics.
So I want to start by saying that I first met Dick in 1984 when I was a young graduate student at Stanford, and he was a young assistant professor, and I was sure that I had a picture from those times. But when I went down in my basement, I discovered that there were these boxes and boxes of old pictures, and so I didn't have time to go through them, so instead I went on the web to look for a picture of the young Bond, and I found one. This is an illustration of the young Bond. I also discovered at that time, though, that we all thought that when Dick went home at 7 o'clock in the morning or whatever, that he was going home to sleep. But in fact, Dick has been leading a separate, a secret life, and he's actually recognized as one of the nation's preeminent authenticators of sports autographs and game used items. Dick never told us that he actually won the much more important prize than Gruber, the coveted grand prize of the first World Series of autograph authentication. But actually, I should say that my experiences with Dick didn't end when he left Stanford in 1984. A number of years later, at Stanford, in fact, Dick guided me through Jim Bardine's classic gauge-invariant cosmological perturbations paper. I don't know if you remember that. And then we struggled desperately through a paper by Hawking on cosmological perturbations, but I think we never really understood. And then he left for CITA, so he didn't end up my advisor. But a number of years later, just when I thought I was heading off to medical school, Dick gave me a job and told me never again to ask one of my letter writers to write me a letter. So, thank you, Dick. So I'd like to talk about, we've been hearing about all the wonderful and fantastic things over the last decade that this satellite has done, that we've learned about cosmology, all the great ways in which the CFE agrees with our standard model of cosmology, and indeed it does, and it's an incredible accomplishment. What we've been able to learn, well, this is a 3-year map, we have a 7-year map, what we've been able to learn from this map. Of course, much of that has come through the idea that what we're supposed to do is expand the map in an angular power spectrum, and that's because our model tells us that that is where the most important information on the CMB sky is contained, and then further on into polarization. Now, I could be telling you I could be here to tell you about the odd deviations from this this angular power spectrum at intermediate L. We can see them. There's a very prominent one at L equals 200, one around L equals 40, and one around L equals 20 in the first year data. And I could be telling you that here to tell you about the fact that those were only there in the ecliptic polar data, not the ecliptic planar data, something that was actually pointed out in one of the early versions of one of the WMAP1 papers. The dip in that first peak did seem to go away, even though there was another experiment that actually saw it, which shared a rather unusual particular property with WMAP, which is that it was the only one of the CMB experiments that looked at the first peak, that looked at large portions of the northern ecliptic sky. And in fact, what it turns out is that that dip is still there. It's actually due to a region localized around the north ecliptic pole, representing about 10% of the sky. There's approximately a 10% deficit in power at the first peak due to a region around the north ecliptic pole. Can't say we understand it. It has a significance somewhere around 0.05, and it's there in every year's data. And we'll be putting out a paper sometime next couple of weeks describing that. I have no idea what the significance is, but it is still there. And all of those three so-called anomalies are still there. I could be telling you about something that we see in the full sky ILC, namely the fact that the quadrupole and octopole, the map of them, consists of a set of 6 extrema that lie essentially along a great circle, perpendicular to the ecliptic, pointed at the dipole, and aligned in such a way, so oriented in such a way around their axis, such that the ecliptic plane very carefully cuts through separates the 3 stronger extrema in the south from the 3 northern extremes in the south. But that's not mostly what I want to tell you about. What I want to tell you about is the angular correlation function. Something that we used to think about at CMB long time ago. And we sort of stopped for the most part, in part because we believe that the angular correlation function contains the same information as the angular power spectrum, just differently organized. And that is true if the angular correlation function is obtained by a full sky average. It's also true in the ensemble if the sky is statistically symmetric, statistically isotropic. The 2-point correlation function isn't actually obtained from a full sky average. It's obtained from partial sky information. But more importantly, it is often true that we take Fourier transforms of data because sometimes it is easier to see signals in the Fourier transform than in the original data, or vice versa. So just because we look at the data in one way doesn't mean we shouldn't look at its transform. So what happens when we look at its transform? Well, this is what happened when Kobe looked at the 2-point correlation function. This is kind of just about the end of the time when people who used the 2-point correlation function very much. And what they noticed was, in their fourth year DMR4 paper, was that the 2-point correlation function, as you can see, vanishes, or is very close to 0, above about somewhere around 60 degrees in all the channels and in the combination map. Now, it's hard, I don't think anyone put a statistical significance on that result. They noticed it, but no one did any particular statistical analysis, and it was mostly forgotten. In fact, Gary will say when he looked at the 2-point correlation function in the WMAP1 data, he said, oh yeah, I forgot all about that. And this is what it looked like in the 1-year data. So you see here is, in red, the Q band, in green, the V band, in yellow, the W band, and in the dashed line, the ILC. All of these on the KP0 cut sky, so outside the KP0 cut. And in the first year, you also see from the full sky ILC that essentially all of them seem to be very close to 0 over some range from about 60 up with this odd anti-correlation at large range. Now, you'll also see that they don't particularly well, agree very well with the lambda CDM model. But on the other hand, we should be careful. That's not what's terribly strange, because as you see, those error bars, although very coarse, you can't look at those error bars and just guesstimate what the significance is. These are highly correlated error bars, but they're also very large error bars. And so the chance that the 2-point correlation function would look this different from the theory is actually relatively large, 5% or 10% or something like that. That is not what's particularly strange. What is particularly strange is that the 2-point correlation function seems to sit very close to 0. So if you like, there's an alternative phenomenological model, which is that the 2-point correlation function is 0 above 60 degrees. And that model, that phenomenological model, agrees with the data to a surprising level. Now, one measure of that was proposed by WMAP. That's the integral from -1 to half of C of theta squared, not the integral from -1 to half of the difference between the theory and the observation squared. Because again, some measure like that of the 2-point correlation function won't be terribly unlikely. This changed somewhat in the 3rd-year data, namely the Q band came into agreement outside the KP0 cut, also became close to 0. What did change is that the ILC, which is now constructed in a different way, no longer looked quite as 0. And the same thing is true of the C of theta that you would get by taking the reported maximum likelihood estimate CLs and turning them into a 2-point correlation function. Same thing true of the 5-year and the 7-year map. In fact, the 2-point correlation function has been, I would say, remarkably stable. The 2-point correlation function outside the galactic cut has been remarkably stable, far more stable than the low LCLs. And I would show a plot about that, but we haven't had a chance. We sent an email about to Gary Hinshaw, and I guess he's had some troubles lately, so he said he'd respond soon, so I'd rather not talk about the details. So how unlikely is this? Well, typical numbers are that if you take the 2-point correlation function outside some conservative, some generous, let's say, galactic mass, that you will get this little 2-point correlation function as measured by S1/2 something like 0.03% of the time. Or if you take it over the full sky, something like 5%. Where the full sky is, of course, from some reconstruction, like the ILC map or the things that George does. We can see that if we look at where is the 2-point correlation function coming from. If we plot it on the region, take only points that are outside the KQ75 mask, and this is from WMAP5 data, we see that it's very close to 0. If we include points that are inside the KQ75, pairs of points, both of which are inside the KQ75 mask, it's a little bit less close to 0. Almost all the contribution is coming from pairs of points, one of which is outside and one of which is inside. Now remember, this is from a map in which the only data that was used to produce it was the stuff outside, not the stuff inside. Is this an accident? Well, if we took the full sky, which already is unusual, remember, it has the chances of having as little 2-point correlation function on the full sky as we see is about 5%. Plus, it is a highly aligned sky, in the way I showed you in that map at the beginning. even then, only about 2% of rotation, arbitrary rotations of that sky would end up putting most of the two-point correlation function in this way behind the galaxy, in the way we see in our sky. What could this be? Well, it could be that so only about 0.03% of realizations of the concordance model have so little cut sky large angle correlation. This could reflect a 0.03% probable full sky two-point correlation function, or it could reflect a less improbable full sky two-point correlation function with less than 1% probable alignments and a about 2% probable rotation of that aligned sky with the galaxy. Now, what George will tell you is, and I hope you agree, George, that direct calculation of the two-point correlation function of the cut sky is suboptimal, and that when we should really use the ILC result, essentially, George's results agree with the ILC result, but essentially reconstructing the full sky ALMs from the cut sky data, and those yield a larger S1/2, essentially the same as the full sky ILC. So there are two responses to that. One I can tell you a lot about, which is that what is odd is the cut sky two-point correlation function. In other words, if that's true, this is what you're talking about. The other is that we believe, and we will, if we're wrong, we will come out and say so, that as far as we can tell, our sky has unusual properties that I'll tell you about in a second that seem to change the usual story. In other words, that we should not rely on the ILC for our two-point correlation function. And those unusual properties have to do with the fact that unlike in the theory, it turns out to be very difficult to get low two-point correlation functions. There's two ways. One is to set all the CLs close to 0. That's not what our sky is. We do not get our sky to have so low a two-point correlation function from lowering the quadrupole. For example, if we fixed all of the WMAP CLs above, from L equals 3 and above, and varied the quadrupole, we could get the S1/2 to be about 8,300, and it's about 1,100. If we also varied the octupole, we could get it down to about 2,500. If we were using the theory, we could get it down to about 1,000, but with the actual data, the quadrupole and the octupole alone cannot get S1/2 that low. In fact, neither can, even if you vary at 2, 3, and 4, it doesn't. You have to vary 2, 3, 4, and 5 in order to cancel the contributions from 6, 7, 8, 9, 10, etc. Okay? That's not true in the theory, but it is true in the data. So we are not getting two-point correlation functions from just low CLs. We're getting it from cancellations between among low LCLs. So, in other words, and this is what, even more so, the disturbing thing about this is that even if we then took all of the theoretical CLs and replaced them by their measured values, you would think then if I took that as my new theory and did realizations of that new theory, that I would recover low C of theta. And that is not true. So if I interpret the low C of theta as a full sky C of theta, and I go and build a theory with those observed CLs, and draw ALMs, and now ask what is the new two-point correlation function, the fact that there's two ways that I can get low C of theta. I can get it from having unusual low fluctuations of all the CLs down to low values, and that will give me a low S1/2. That's not what we see. But about 3% of the time, you can get that. But if you look for cases in which what actually happens is what happens in our sky is this cancellation between 2, 3, several of the multipoles among each other, that seems to essentially almost never happen. So if you believe the reconstructed full sky CMB, there are signs that the sky is not specifically isotropic. Namely, we get aligned quadrupoles and octupoles that seem to be connected to the solar system. If we look just at the CMB outside the galaxy cut, then it seems to lack large angle correlations, first seen by Covey at about the 5% probable level. So if you take the statistic, divides by WMAP, and go back and say, well, how bad is Covey? It's It's about 5%. Now, yes, that's a posteriori in the sense that no one did that back then. I don't think it depends very much on statistics, at least when we try instead of a square and absolute value, it didn't matter very much. So maybe there's some other statistic which wouldn't see this. But now it's much less probable. In other words, the probability that we would see it go from the 5% to what we see now is less than about 1 in 200. Not what you'd expect from just a strange fluctuation compared to what we originally saw. Okay, this could be due to a statistical fluctuation, it's unlikely. It could be due to topology, but that's not yet seen. And as Andrew pointed out, Jackie pointed out to us yesterday, you can't just explain this. You have to explain all the full two-point correlation function. It could be due to features in the inflaton potential, but that's not just contrived, but has a very low chance of actually reproducing such a low S1 hat, even if you put just saying. So, while the cosmic orchestra may be playing the great inflationary lambda CDM symphony, the bass, cellos, tuba, and timpani seem to have the wrong score and are carefully conspiring to hush it all up. Thanks.